So a common misconception amongst the NESI board is that you can only drive devices that work with 5 or 6 volts. That's actually not true. I have here a 9-volt switching step-up regulator that I got off Pololu, and I also have a 12-volt one. That's, I think, about as high as they go, but you could probably find higher current ones. So we're just going to demonstrate the use of this 9-volt one here by plugging it into a breadboard. Now, you'll see on the back of here that it actually labels V in, V out, and ground. I don't know if you can see that. So we're just going to take that and we're going to plug it into the breadboard here. And we can go ahead and attach a yellow wire. We're just going to use a yellow jumper wire from the 5-volt pin on the NESI board into the V in on the step-up regulator. So the V in would be the bottom pin. And then we'll also attach the ground pin on the NESI board to the ground pin, or the common pin on the step-up regulator. And now, if we wanted to connect a device or something, we would use the V out pin, which is the very far upper pin, right here. We could use that pin, and then the center pin. Oh, I did that wrong. You'd use this pin right here, and then the center pin as the common, or the ground. So if we wanted to connect a motor or something, we could then see 9 volts as the voltage across the blue and the white wire, which we just connected. So we can demonstrate that by connecting the blue and white wire to a multimeter here. Here's our 9-volt source. So that's 9 volts. And if we take a multimeter here and set it to a DC volt setting, and if we plug the NESI board in, we can then hook up the red lead to plus, and the white lead to the common, or the ground. And we can see that there's 9 volts going through that. So you can get these regulators off of pololu.com. I'll put a link in the description, and you can go check those out and use them to drive the NESI board to drive devices off the NESI board at a higher voltage. So in case you're wondering how a switching regulator turns that 5 volts into 9 volts, the circuit schematic looks something like this. Now, this switch right here is oscillating back and forth. It's opening and closing many, many times a second. So, as we know, we have a few graphs here. Although these graphs look pretty similar, they're actually not that related. The first one here states that as the more amps we draw, or the more current is drawn in a circuit, the less volts will be present. So out of an open circuit right here, if you have plus 5 volts and ground right here, and you were to measure the voltage across these 2 points, it would measure 5 volts because no current is being drawn. It's at this point in the circuit. So this is an open circuit. Now, when we short these 2 points, like that, when we short 5 volts and ground, if you were to measure the voltage from here and here, it would measure 0 volts. Now that's because this is one piece of wire, and the maximum current is being drawn, which is right up here. It's a short circuit, and the maximum current is being drawn, and 0 volts are present. Yeah, that's really all you need to understand for that particular graph. For this graph, this compares the 2 volts versus amps in a different way. This states that the more volts we force through something, the more amps it's going to draw. So if we have a 5-volt DC motor, let's say this is 5 volts, then it's going to draw a certain number of amps. It's going to draw a certain amount of current. Now, if we were to force 9 volts through that same motor, it would draw much more current. That's just a property of devices. When more voltage is forced through them, they tend to draw more current. That's the same reason why you'd need a current limiting resistor on an LED. Now, back to this circuit here, this switch closes. Let's go through this step by step. The switch closes, creating basically a short right here. So as we know, the current going through here, it's going through like that. It's at the maximum amount of current available. And if you were to measure the voltage at those 2 points, you would notice that they'd be at 0 volts because the maximum amount of current is actually being drawn. It's a short circuit, so there's no volts. Now, while that current is being drawn, because it's an inductor up here, this is an inductor, by the way, it's actually creating a magnetic field. Now, the magical property about inductors is that they resist changes in current. So when this switch closes, as soon as this switch closes, the current is no longer flowing through here, and now the current is going straight across. Now, this right here is more or less an open circuit. There might be some resistance in there for some kind of a load, but more or less it's an empty circuit. And the inductor over here uses that magnetic field, which it's built up, to try and resist that change in current. So here we can use our second graph here. So the current, it's drawing, let's say, around this much current. Now, when that circuit opens, this amount of current actually drops. It goes down to 0 because we're not drawing any current. Now the inductor, trying to resist that, uses its magnetic field to try and raise that. So the inductor attempts to raise its volts. It attempts to raise its volts in order to attempt to raise the current back up to its original, however much current it was drawing. Now, this actually ends up being much higher than the original voltage. So this inductor has now efficiently stepped this 5 volts up to 9 volts in order to resist the change in current when we opened this circuit. Now, our load has 9 volts, but you'll notice that as soon as this switches off, it won't have any volts here. So we go ahead and add a capacitor here. And while this 9 volts is being supplied, this capacitor is charging, and it's charging to 9 volts. So as soon as this switch closes again, there's also a diode in here, I forgot. This capacitor won't just short to ground because there's a diode right here. So this capacitor will instead provide, when this is actually closed, this capacitor will provide the current. So as soon as this switch reopens, this capacitor won't actually provide an entire 9 volts. It'll provide less than 9 volts, but it's negligibly less. So as soon as this switch closes again, it's supplying 9 volts again, and it's already charging this capacitor. So the graph of the voltage over time might have some fluctuation in it. It might look something like that, but that's a negligible difference, and really it provides a moderately constant 9 volts of energy.